Hello. Today I'll be speaking about why choose the GateMate FPGA. This is the first time I'm giving the talk, so if I make any mistakes, please forgive me and correct me. Hello. Today I'll be speaking about why choose the GateMate FPGA. This is the first time I'm giving the talk, so if I make any mistakes, please forgive me and correct me. On the slides, you can see the links to the ULX 5M Discord server and the LMX GateMate Discord server, two different boards. So if you're currently using a FPGA manufactured by TSMC in Taiwan, your production is at risk. On the left-hand side, we have an image of the undersea cables connecting mainland China with Taiwan. In 2023, two of the cables in the upper left-hand corner were cut where the X's are. In 2024, another cable was cut. This time, the Coast Guard responded very quickly and chased off the Chinese vessels before any more cables were cut. And I don't think it's just accidental. If you look at the right-hand side, you can actually see an image from a patent recently filed by the Chinese, and they're actually doing research on how to cut cables. So if you look at the statement at the bottom from their foreign ministry, Taiwan is a sacred and inseparable part of China's territory. So the position's pretty clear. And it's not even about invasion. All they have to do is surround the island, use anti-ship missiles to shoot down any freighters that try to approach the island. And in 6 months, well, you're not going to be getting your ships out of TSMC. So it's a really good idea from a risk perspective to use a European-made GateMate. So my interest is in sort of system within a chip. You've got your application logic, but you also, when your state machine gets too complex, it's nice to use a software CPU. A lot of people use RISC-V CPUs, but I found that the J1 Mi-Cris Spice family of CPUs are really much smaller. And of particular interest to me is using a small microcontroller such as the Raspberry Pi 2040 with an FPGA. So I'm currently using the open source PicoIce. You can click on the link. Very nice, very sort of solid, stable, strong community. A great way to start using these two, an FPGA with a microcontroller. But the ICE 40 is a bit underpowered, so I need a larger, faster FPGA, which is what brought me to the GateMate. Here is the diagram of the Hanuman stack machine. And then when people always ask, how do you compare it to RISC-V? Well, the RISC-V has 32 registers. Okay, so if you're building a register machine on a device with 4 input LUTs, you have to have multiplexers. So on the left-hand side, we can see a multiplexer between 32 bits, maybe the 0th bit on the 32 registers, right? And so on a 4 input LUT, one lookup table can differentiate between 2 bits. So on the left-hand side, we see the left-hand column. We have 32 bits coming in. Then there's 16 4-input LUT multiplexers, and then we've got 8, and then 4, and 2, and 1. So that comes to 31 4-input multiplexers. So to choose between 32 32-bit registers, you need 996 LUTs. To choose between, for 2 arguments, you need 1,988. And if you look over on the right-hand side, okay, 4-input LUTs are not that big, but they've got some other logic and stuff, carry logic and output latching and selection. So it ends up using up a chunk of real estate. So in practice, what people do, so on an ASIC, it's not a problem, right? Because you can have dedicated hardware that does this multiplexing. It's very efficient. But if you're using 4-input LUTs to do a 4-input bit multiplexer, you have to end up using 3 of these, and it's kind of wasteful of space. So in practice, what people do is they store the registers in some RAM, but then it takes an extra clock cycle, unless you're doing a pipeline system. But for small RISC-Vs, it takes an extra clock cycle to access each one, and maybe an extra clock cycle to write back. So it just slows things down to use a RISC-V on a device with 4-input LUTs. So you really should be using stack machines. They're much more appropriate for this technology. Ideally, what you'd like is something with an 8-input multiplexer, right? And so we see that on the left. GateMate actually does include 8 input multiplexers. So if all of that worked correctly, with 32 bits, um, four of these 8 input multiplexers would bring it down to one 4 input multiplexer, and you'd have 32 bit selection. So this would be an awesome advantage for the GateMate device. But sadly, it doesn't work. The 8 input multiplexers, they have routing, and to save space, the routing can flip the bits. And that's fine if you're using something that unflips the bits, but if you're just using a straight multiplexer, it's a problem. And so in practice, this doesn't work. So it'll be really good if on their next mask rev, they actually did the 8-bit input multiplexers correctly, and then there'll be a really strong competitive advantage, particularly for RISC-V. Instead, their 4 input multiplexers work fine, and that's the same as a 6 input lot, where you have 4 values and 2 control bits. So either one gives you the same effect. And you can see that to do then a 32-bit multiplexer with the Cologne programmable elements using their 4-bit muxes, basically 32 signals come in, you have 8 CPEs, brings that down to 2 CPEs, brings that down to 1. So that's 11 Cologne programmable elements, as opposed to 31 of the ICE4s on of the 4 input LUTs on any device that uses 4 input LUTs. So I think GateMate's really interesting for RISC-V devices, which kind of what brought me to it. Okay, they also have these curious things called LUT2 trees. I was quite confused by this, and it turns out this is completely separate from the multiplexers. And what is a LUT2 tree? Well, it's just a basic Boolean logic, right? So here we have AND, OR, XOR, NAND, NOR gates, and each of these has 2 inputs and 1 output, right? So that's basically what one of these LUT2s are. And so if you look down in the middle at the bottom, there's good. If you have like A, operation B, operation C, operation D, with parentheses, then that kind of stuff just works perfectly on their 4 input LUTs. What does not work well is if you have A and B or C and D or A and C. So there's crosstalk with the A and C, and then that doesn't work very well. And also if you're doing A question mark B colon C, that also doesn't work well on these. So you can actually do a table of all the different inputs, right? So if each of these truth tables has a top row and a bottom row, you can lay out for the top row and bottom row. And so if they're all zeros, that's like a constant 0. If they're all ones in the bottom right-hand side, constant 1. We've got NANDs and NORs and XORs and some other logical operations. So you can actually think about this. And a lot of the electrical engineers do think sort of in terms of these and combining these operations in terms with sort of parentheses around them. So if you're doing like the good example here, then everything's fine. And if you're not, then supposedly you can use 2 of these 4 input LUTs, kind of like a 5 input LUT, and then that'll be the same as any 4 input LUT lookup table. So I haven't persuaded myself that this is true. You can click on the link to see the arguments, but it's probably true. I'm sure it's true, actually. The other thing they did that I thought was really intelligent is, they have these block ramps, and you can use them separately, or the vertical columns, the thin vertical columns of the block ramps, but they also have hardware, so you can treat this as 4 large RAMs. So I think that was a really good, very flexible. I really like that design choice, right? Particularly for like the stack machines, I can run 4 stack machines on this device very happily and not pay the multiplexer price because it's all hardwired, the access to the 4 large memories. Very nicely done. They also have these 2-bit multiplexers, which was a bit confusing to me at first. So on the middle, we have 7 by 11 in decimal. On the right, we have it in binary. And so basically what you do is you do partial products. So each 2 bits gets in the top row and the bottom row gets multiplied by the 2 bits in the other row, and then you add them all up, right? So you actually have a bunch of, so to multiply 4 bits, 2 sets of 4 bits, you have 4 multiplies, but you also have a whole bunch of adds. How many adds do you have? Well, let's take a look at the adders. The These are 1-bit adders, just to remind you. So basically, you have 2 bits that come in that you're adding. You have 1 carry and 1 carry out, and you have the sum out of the bottom, right? So it's a 5-port device. And what they do that's really nice is they string these together horizontally and vertically, right? So it's basically hardwired adders, if you can do the routing correctly. But so I really like that you don't have to do a lot of routing to connect the adders together. 2 of these adders fit inside one colon programmable element, but the routing software doesn't care; it just lays them out. And ripple carry adders are really quite fast, reportedly. So how do we do these adders? Let's take a look at 8-bit multiplies. On the right, you can see the different partial products and shuffle them vertically just to make it easier. So just on the addition on the right-hand side, let's start on the right-hand column. So the lowest 2 bits, there's no addition there. That they just go out. So there's no carries. The third column, you've got 3 bits that you have to add. So no carries coming in and 1 carry going out. So the next 4th column, you've got 3 items you have to add and 1 carry. So it takes 2 additions. So you add the 3 and you get the 1 bit, and then you have to add that with the carry. So that takes 2 adders. Anyhow, you can go through this whole thing and double check it. And on the bottom row, you have the number of carries and the number of adders. Those are just 1 digits, right? So each digit is just the number of carries in that column. So don't think of it as 54, 32, 10. Think of 5, 4, 3, 2, 1, 0. And so maybe I did this wrong. If somebody checks it, that would be great. But I count that, so to multiply 2 8-bit numbers, that's 16 multiplies, and 53 adders. So 43 colon programmable elements. So you get like 20,000 colon programmable elements. So from that, you can figure out how many of these multiplies you can do. But these may be off by some small number. So please, I tried to cross-check it, but please somebody else cross-check it. The other thing I really like about this chip is the clock domain crossings. When you're trying to use a microcontroller with an FPGA, you're going to have clock domain crossings. You could buy a system on a chip but those end up being much more expensive, much cheaper to use separate ones. And also you get way more software, like on the Raspberry Pi. And so these FIFOs are great because one clock domain can send stuff in at one clock speed, the other clock domain can pull it out at the other speed, and everything works just hunky-dory. And so they've got all of this in hardware, which also means they don't have to debug any Verilog, at least way less Verilog. So this is maybe the thing I find most attractive about this particular chip. I also think the multiplication is interesting, that one can do some very creative stuff with this. The other piece I really like is how they make their masks. So they sort of have these FPGA cores, and they have a whole bunch of these on a mask with like 1,000 wires between neighbors. Kind of looks a bit like a transputer, actually, now that I think about it. And they can cut out 1, they can cut out 2, or soon they'll be able to cut out 4, 8, 16, 32, as many of these as you want. And so because they only have 1 mask set, it's much less expensive. So I think this is a really brilliant design thing. And I'm looking forward to running hundreds of these sometime soon. Of course, if you get hundreds, 1 or 2 may be bad, but then you just route around them. So anyhow, we'll see what happens. So the mainstream board is the 50 euro Olimex GateMate board. It has a whole bunch of peripherals. What I really like, it's got both in the middle. Here you have the Raspberry Pi 2040, and you've got the GateMate. And 28 wires, really critical, the number of wires between the two. I also really like that it's got 2 PS RAMs. Excuse me. That's perfect for memory, right? So for video display. So while you're displaying from one of them, you're writing to the other, and then you swap. So really good for video applications. I'm not so excited about the VGA and PS2. I'd much rather have USB and DVI, HDMI. And fortunately, they're now building somebody else is now building a whole bunch of GateMate add-on boards. So you're going to have analog to digital, I2S audio, microbus, 2 USB host ports, camera port, DVI, Ethernet, power, timer, simple I/O. So it kind of makes there's a very rich environment, all the key stuff that you need. I could be using something like the $60 Ice Sugar Pro, but the problem is it doesn't have the Raspberry Pi peripherals, right? So then it's a bit more expensive. Plus, I have to do a whole nother board, and I just want everything on one board. I'm a software developer, not a hardware guy. There are a bunch of these. So there are three of these boards that connect a Raspberry Pi with a FPGA. There's a Pico Ice on the left-hand side and the Ice-V wireless. The Pico Ice has some 12 wires between the two. Olimex has 20. I'm not quite sure about the Ice-V wireless. Basically, you have to use the four. You basically use the four QSPI ports in and four QSPI ports out. So I guess that comes to 8. 10, sorry. And then the other thing I really like about the GateMate is this 20 bits, right? So for 16 bits on the ICE40 5K devices, which is kind of how I use the memory, that's fine for music or sound processing. But for real-time control, you often want to be down at the 20, maybe 22-bit level. And so I thought it was really smart that Olimex provided that memory in that width. They didn't go with 1, 2, 4, 8, 16, 32. They went with 1, 2, 5, 10, 20, 40. Really smart move on the designers. And although I mentioned 0 on a large RAM, really their RAM can either be used as large RAM or as block RAM. So I think that was also very nice design. And then tons of these 8x8 multipliers. So I want to do a vector processor, coprocessor. So their board is really good for that type of work. Doing lots of large vectors. And then they also have a case, which I really like. The column on the right is the Ice-V wireless. So if you want to use the Ice 5K with a wireless ESP, then that's a good choice too, but a bit more expensive. A couple of boards not yet shipping. Sorry if it got cut off. Pico 2 Ice is going to have the Raspberry Pi 2350, which gives you an HSTX, really basically DVI kind of HDMI without the audio port, which is really good. But it still has the Ice40, which is too slow. So they're actually doing, on the right-hand column, they're doing Pico 2 NX, which has a much faster, larger 17K logic elements and 2 CSI D-PHYs for cameras. ULX5M is also, it's going to have the Raspberry Pi 4 baseboard. And also these GateMates have 130s on them. So anyhow, so here's what the ULX5 board is going to go on, and it'll go on the Raspberry Pi Compute Module 4 form factor. So you can get in 32 different configurations with Wi-Fi, without, with RAM, 1 gigabyte, 2 gigabyte, 4 gigabytes, 8 gigabytes, or with an EMC that's like a little disk drive, a removable drive, either without or 8 gigabytes, 16 or 32 gigabytes in the baseboard. So great, all good. Actually, I kind of like just the Raspberry Pi 2350 is fine. I don't need the 4. That's kind of overkill. But, I'm not a board developer, so I use what I can get. There is the sister board, the ULX4M, which has one of the lattice chips on it, or actually, there are 2 different baseboards that it works with. And so the idea is that the ULX5M will also work with different baseboards. So sounds good to me, because everybody needs different peripherals. The other good news is that Cologne Chip is contracted with EOS's headquarters to port NextPRN to the place and route to the GateMate FPGA. You can click on the link. When last I checked, it was 55 commits ahead of the master branch. And they got 2 engineers working on it, one from each of the companies, maybe some more. There are 2 parts. One is the sort of cleaning up the NextPRN, make some high-level changes. They need to get data from the chip to drive the place and route, and then there are about 28 primitives which need to be supported. So I also created an awesome GateMate repository. You click through there and see all the good stuff that there is available for this board. Links to good resources. If you have any questions, Lozinski at pythonlinks.info. Thank you very much.